Hello everyone, I'm Udit Agarwal, and I will be presenting our experience paper on generalized concurrency testing. This work was conducted by people from Microsoft Research, University of British Columbia, IIT Hyderabad, and IIIT Delhi. Exploring concurrency is fundamental to building scalable systems. It can range from desktop applications with multiple threads that exploit a multi-core CPU, or a giant distributed system with multiple processes spanning across virtual machines. In either case, getting the concurrency right is challenging. The combinatorial explosion of possible interleavings between concurrent actions makes it even harder to find bugs or even reproduce known ones. Moreover, concurrency bugs can occur in many forms like data races, deadlocks, live locks, atomicity and order violation, etc. And these bugs can be quite dangerous. For instance, Flexcoin, a once popular Bitcoin wallet, had to shut down their operations after an attacker robbed Flexcoin by exploiting a concurrency bug in their production code base. Common industry practices for finding concurrency bugs mainly rely on stress testing. However, stress testing is often inefficient and its ability to get coverage of interleavings is unclear. Due to these inherent non-determinism involved in stress testing, we cannot use it to reliably replay a concurrent bug. And so debugging concurrency bugs is no less than a nightmare for the developers. Due to these disadvantages, prior work has advocated for systematic concurrency testing, which takes control of all the forms of concurrency within the program and conduct a systematic search within the interleaving space. With systematic concurrency testing, developers also have an option to create an abstraction of the program's enormous interleaving space and then test only the abstract program space. Now, concurrency in a program can manifest in various forms. It changes with the underlying programming language and the programming model used. Concurrency also depends on the programming framework that we use. For instance, Azure Service Fabric, which is a distributed systems platform for deployment and management of microservices, has very different concurrency semantics from, say, libevent, which is another framework in C and C++ used for asynchronously receiving callbacks. With all these different forms of concurrency, it becomes infeasible for the developers to engineer systematic concurrency testing tools that supports the variety of concurrency semantics that we have. Prior work on systematic concurrency testing address only a specific type of concurrency and are difficult to extend to other forms of concurrency. For instance, Chess, a C#-based systematic concurrency testing tool, supports only a subset of C# threading APIs and cannot be easily extended to support tasks or async-await concurrency primitives, both of which are widely used in C# nowadays. Moreover, large software systems might also use multiple concurrency models simultaneously. For instance, Memcached uses both thread-based and event-based concurrency models simultaneously, and so existing tools cannot be used for systematic testing of Memcached. This gap between what is required to do systematic concurrency testing of complex softwares versus what is being offered by existing tools motivated us to put forward the idea of generalized systematic concurrency testing, which aims to democratize testing by allowing developers to build their own systematic testing solutions, irrespective of the programming language, framework, or the programming model used. So in this work, we propose Nekara, a cross-platform open source library that provides simple and expressive APIs that developers can use to model concurrency primitives that they have used in their program, irrespective of the programming language or framework. Nekara encapsulates a cooperative scheduler along with various search heuristics from prior work, like random and delay-bounded scheduling, and thus freeing the developer from having to redesign these themselves again. Nekara can also record scheduling decisions and provide full reproducibility for concurrency bugs. In this paper, along with the Nekara library, we also shared our experience of using it for several case studies, including production services from Microsoft, and that Nekara has already been adopted in practice within Microsoft. So unlike prior work, Nekara delegates modeling as well as injection of these models to the developers. So Nekara has an abstract and uninterpreted notion of operations and resources, where operations generalize the idea of a worker, such as a thread, task, or actor. Resources generalize over synchronization primitives, like semaphores, mutexes, or conditional variables. Developers can map these operations and resources using Nekara APIs to the concurrency model of their interest. Additionally, in most cases, applications depend on a well-defined framework or library to provide concurrency support, for example, pthread. Developers can then design models for the framework APIs that they have actually used in their program while keeping the rest of their software unchanged. And after modeling, developers can simply reuse their existing stress test cases to leverage the systematic testing engine and search heuristics provided by Nekara. I will now give a short example of how Nekara APIs can be used to model concurrency primitives in a program. So consider the following program. There are 3 concurrent threads, all executing the function foo and trying to update the value of a shared variable x. Clearly, the assertion here can fail, but only in a specific interleaving where thread 1 is the last to update the value of the shared variable x. For this program, it makes sense to map threads to Nekara operations and locks to Nekara resources. Because Nekara performs cooperative scheduling, implementing synchronization is fairly easy. So to model mutex acquire function, our mock first does a context switch to give other operations the chance to acquire the log, and then goes ahead to grab the log if it is available. When the log is not available, the operation blocks on the corresponding resource. Mutex release function is also fairly straightforward, where the currently executing thread will signal the resource and possibly context switching with any other thread waiting on that resource. Development of these models does require some expertise in reasoning about concurrency, especially for understanding the semantics of synchronization APIs and encoding them correctly using Nekara resources. But after modeling, developers can simply use their existing stress test cases to leverage the systematic testing engine provided by Nekara. We show the effectiveness of Nekara by documenting several case studies, both with open source software and Microsoft's production services. Each time showcasing that modeling concurrency for integration with Nekara requires minimal effort and provides significant value for testing. We found new concurrency bugs and also reproduced known bugs to contrast Nekara with existing concurrency bug finding tools. Finally, we also share our experience of Nekara's adoption in Microsoft for testing Azure production services. So moving on to our first case study with Memcached. Memcached is an open source in-memory key value store, which is commonly used as a cache between application and a database. It is mostly written in C and is highly multi-threaded. There are 3 major data structures in Memcached, which are accessed concurrently by multiple threads. And to make things more interesting, Memcached simultaneously uses thread-based and event-based concurrency models using pthread and libevent libraries. To integrate Nekara with Memcached, we modeled the basic functionality of pthreads and libevent. And like instead of modeling the entire library, we only modeled the APIs which are actually being used in Memcached. It took us about 2% week of effort, and we also had to mock system calls like socket read and socket write to take control over network traffic coming from Memcached clients. Existing Memcached test cases did not exercise all sources of concurrency within the program. And so we also had to write some new test cases ourselves to run them with Nekara. So we found 4 new concurrency bugs in the latest production version of Memcached. One of these bugs was a non-trivial deadlock bug between three threads, and another one was an atomicity violation bug that caused a null pointer dereference. The rest of the two bugs were due to incorrect usage of pthread APIs. All of these bugs are confirmed by the developers, and these were there in the code base from last 4 years and went unnoticed by stress testing. With Nekara, we were also able to reproduce concurrency bugs exposed by prior work, and compared to stress testing, Nekara covered 4 times more unique thread interleavings in the same number of test iterations. Our second case study is of Task Parallel Library, TPL. So TPL is a library provided by .NET for building concurrent applications, and TPL exposes several key types, such as tasks that interoperates with async and await keywords in the C# language, which are used for writing asynchronous code without the complexity of having to manage the callbacks. We designed a drop-in replacement library for TPL that provides stubs and subclasses that overrides original TPL types. So basically, any existing C# application that uses TPL for its concurrency simply needs to replace it with our Nekara's TPL mocks to get systematic testing for free. It took us about 4% week of effort to mock a TPL library, and Azure developers then used our TPL mocks to test 2 production cloud services of Azure. Both of these services have now adopted Nekara in the regular testing framework. So the first Azure production service, Cloud Supply Chain Service, provides HTTP REST APIs that clients can use to create and manage supply chain processes. It is designed with a typical microservice-based architecture in mind, where multiple stateless microservices coordinate with each other through shared state maintained by the backend storage system. All this mechanism requires complex synchronization logic between the microservices. Azure developers use their existing test cases along with Nekara TPL mocks and found 4 new concurrency bugs in the production version. 2 of these bugs were race condition, 1 order violation, and 1 liveness violation bug. These bugs could have caused permanent data loss or even inconsistent data between databases. The second Azure production service, Azure Coding Service, consists of multiple instances of synchronization processes to provide geo-redundancy to protect against catastrophic data center failures. The developers of this service used their existing stress test cases along with Nekara's TPL mocks and discovered 1 critical race condition bug in the production code base. The developers of this service now use Nekara regularly in their code review and continuous integration process. I will now summarize our experience of using Nekara with the various case studies that we have presented. So we were able to integrate Nekara testing with several systems with no change to the production code in most cases. Only in the case of Memcached do we have to modify the code in order to mock system calls related to socket so that we could write unit tests with multiple concurrent clients. The fact that production code need not take any dependency on Nekara is important for the utility of our approach. As far as modeling is concerned, the overall modeling effort was small to moderate. Development of models does require some expertise in reasoning about concurrency, especially for understanding the semantics of synchronization APIs and encoding it correctly using Nekara resources. However, these modelings are application independent, and modeling once done can be reused across teams, leading to developer productivity. In terms of bugs, Nekara helped catch several interesting bugs, including liveness bug, deadlock, memory leak, as well as functionality bugs like data corruptions. Many of these would not have been caught with existing practices like stress testing or code review. Regarding test cases, we restate that developing good tests that exercise concurrency in a system and assert something meaningful are crucial to get benefits from systematic testing. For Memcached, we wrote a generic test by simply combining existing test cases. For other case studies, developers of those systems were able to write tests themselves without our help. At last, concurrency bug replay and detailed logs provided by Nekara were very well appreciated by the developers. I will now conclude my presentation by highlighting that systematic testing holds promise in changing the way we test concurrent systems. In this work, we presented Nekara, a simple library that decouples concurrency semantics from the testing engine, and thus allows developers to build their own systematic testing solution, irrespective of the programming language or concurrency model used. We showed several case studies on open source software and Microsoft's production service, where Nekara made a considerable impact in terms of the new concurrency bugs found by Nekara and the enhanced developer confidence due to concurrency bug replay provided by Nekara. Nekara's source code and artifacts associated with our work are open source and can be obtained from the following GitHub repositories. With that, I will now thank you all for listening to my presentation, and I'm open to questions now.